Hey guys, today we're gonna simulate a frequency selective metasurface using Luminescent AI FDTD. This example is similar to the one on Tidy 3D where we have a metallic cross pattern in a periodic array on a dielectric substrate. So we will use Luminescent FDTD, which is free of charge, to see if it can replicate results from this industrial solver from Tidy 3D. So let's get started. So first we go to Luminescent repo on GitHub. The link is shown here. It's also linked below in the video description. So as you can see, there are various examples ranging from metasurfaces to photonic integrated circuits to microstrip circuits. So everything governed by Maxwell's equations, right? So if we click this FSS example, that takes us to Google Colab, which is a free Linux environment that you can run free of charge on Google's cloud. So obviously, if you have your own Linux machine, you can also install our freeware there. Yeah, so this is just your typical Python notebook. The first cell is an installation script, which will be provided to you free of charge once you fill out our new user form at Google Forms. And so we love to see what our users are doing with our software. Once you run that, if you're using your own machine, you only need to install it once, obviously, right? If you're using Google Colab, then you need to install it every time, but it only takes a couple minutes. So in our Python script, we first import both Luminescent and GDS Factory. So GDS Factory is a free software from Google, which allows you to create planar patterns in Python for integrated circuits and other things. If you have your own GDS file, you can import that into GDS Factory, or if you have cat files like step or STL, you can import that directly into Luminescent. So we're pretty flexible there. So the first thing to define is your simulation path folder. So everything like the problem description and the simulation results will be dumped to that folder. And you can take a peek inside after you run the simulation to see the different data. First, after that, we define our frequency, which is from 10 to 14 gigahertz. So our philosophy is to not force you to do, anything specific with regards to units. So you are basically allowed to use whatever length or frequency units you like, as long as they're consistent. So in this example, our frequency is in gigahertz, and our length unit is in millimeters. And what happens on our backend is we normalize everything with respect to the central frequency. And then the time is normalized with respect to one period around that frequency. So that way, you can simulate everything from photonics to terahertz to RF. Next, we define our unit cell geometry parameters, and these come from the Tidy 3 examples here. So there you have it. Here, I also add plenty of air gap above and below the metasurface because it's a metallic structure with some resonant frequency, right? So it's going to have a pretty big reactive zone where the fields are oscillating back and forth. So we want to keep that from coupling into the PML on boundaries. Next, we define our mesh resolution. So one of the greatest things about our software is adaptive meshing, where we increase the mesh resolution around key features like thin metallic layers and gradually um, taper them to much bigger cell sizes once we reach empty space. So this allows us to dramatically reduce the number of mesh cells that we need and reduce our computational load. So this feature is generally available in the commercial solvers like Tidy3D and Lumerical, but it's absent in most of the free FDTD software like Meep, right? I mean, I think Meep is as you may know, is open source FDTD package. Um, I mean, I think it's got a lot of features. It's pretty accurate. But I think one of the biggest disadvantages is it only uses uniform cell sizes. So it doesn't have adaptive meshing like ours do. So that makes it pretty much impossible to simulate thin metallic films like we are doing here. So our software is both free and it also comes with all the bells and whistles of a industrial grade solver. Anyways, okay, so here we use a pretty coarse resolution of zero 0.4 millimeters dx, and then we use that to define kind of this higher relative mesh density for our metallic layer. So then we create our geometry in GDS Factory. Pretty self-explanatory here. So note we only make a quarter section because the problem is symmetric. So if you look at it, the pattern is periodic, and we have a x-polarized plane wave. So we have EX going in the horizontal direction, which means our boundaries on the X sides are pec or odd symmetry, and our boundaries on the Y sides are even or PMC boundary. And then in the Z direction, we want the signal to go in and go out. So those are radiative or open, or what we call PML. So that's our planar pattern. To make it 3D, we define our layer stack. So here we have a thin metallic layer, your copper trace. In this regime is pretty much a perfect conductor. So we call it PEC. You have your dielectric layer whose epsilon or relative permittivity we set here. We also set our background material to air, and we set the higher resolution around the PEC layer. So one thing to note is, so dx is only the horizontal resolution, roughly speaking, of the metallic layer. Um, so so it's only 0.1 millimeter thick, right? So in the z direction, the resolution is actually higher than that, because our software will automatically detect that there's a very thin metallic layer there. So we can, so just know that's done automatically for you. Then we make our problem. Uh, so you have your simulation folder path here. Self-explanatory. The keys are the S params, or the flux S params, or the modal S params that you want to calculate. So here we call our mode 0 this EX polarized plane wave. Uh, so EX is 1 and HY is 1. So in our normalization system, the free space impedance of 377 ohms gets get normalized to 1. So that's why you have both EX and HY as 1. Yeah, because when you do the normalization with respect to the central wavelength, everything becomes nice. Yeah. Um, you know, Whereas in 3D, in tidy 3D, they force you to use their unit system, whether you're in photonic, or whether you're in photonics or RF. But for us, I think we take a more natural approach to normalization, and let you use whatever units you want. We then define our ports, which is essentially just a big plane monitor above and below the metasurface structure. We set RSD margins, materials, layer stack, relative Cron numbers. So our Cron number is calculated kind of with respect to the average cell size. Now this problem has very thin features like this metallic film, and that can create extra instability. And it's also a feature that's smaller than the average cell size. So for this problem, we actually set our relative Coulomb number to be lower than 1. Um, don't worry about it. If your relative Coulomb number is set too high, um, our software will detect the instability automatically and lower it for you, and lower the Coulomb number for you. So this field decay threshold refers to the fact that we are blasting with this Gaussian pulse containing our necessary frequencies. Um, so after a few periods, all the energy will dissipate from the system, and that's when we stop the simulation. So 0.03 refers to stoppage of simulation when energy has decayed to 0.3% of their maximum. Save at 0.5 means we save a simulation movie frame every 0.5 periods. Lumi.solve simulates the problem. Ta-da! So as you can see here, it's super quick. So even your good old laptop can do this, right? Because this was done on the free CPU course on Google Colab, so it's pretty bad. So there's only two CPU cores on a free Google Colab, and and this thing still ran in like under a minute, which is pretty amazing because we've um, taken special care to mesh this properly, to really reduce the computational load. Whereas Tidy 3D, they have their super expensive GPU clusters, and they make you pay for it. So they basically use, I mean, look at the resolution that they use, right? It's really ridiculous. I mean, I think they're using like 10x the resolution that we are using, and because FDTD scales as the fourth power of the resolution count. So the computational resource that went into the Tidy 3D example is literally like 100x or 1000x than what we used here, and yet we are able to replicate their results pretty well. Yeah, so we plot our lovely frequency domain results. So once we invoked Lumi.solve, all the simulation results got dumped to the simulation path that you specified. So we load our solution from there and plot it. So we have our resonance at around 11.8 gigahertz, 3 dB loss at around 10 gigahertz, pretty lossless at 14 gigahertz, 10 dB bandwidth of maybe around 0.8 gigahertz. And if you look at Tidy 3D's results, it's a pretty good match. I say the resonant frequency is off by maybe 0.1 or 0.2 gigahertz. So that's like a 1 to 2% error. That's not bad since we're using like 1000x less computational resource than them. The attenuation at 10 gigahertz and lack thereof at 40 gigahertz, those two values match almost exactly. Though the 10 dB bandwidth, I think theirs is a bit tighter than ours. Maybe because we're using such a coarse resolution that it kind of sometimes it broadens the peak a little bit. But overall, the results are in excellent agreement with Tidy 3D, which is infinitely more expensive than ours. Because Tidy 3D makes you run everything under cloud and pay for it, whereas our code it's free of charge, and it runs even pretty well on CPU for simple problems like this. Okay, so there you have it. Please, if you have any questions, just shoot me a note in the comment section. So yeah, so everyone can can see it, and I can respond to it. If you have a private question, you can shoot that message to me and my company, and the contacts are shown here on the GitHub page and also linked below in the video. I just wanted to say one last thing about our software. So we are named Tidy. So we are called Luminescent AI, and it's not only an FDTD package, but also a generative AI that's capable of designing metasurfaces and photonic integrated circuits and microstrip circuits based on your specification. So in our next video, which is coming up in a few weeks, we are actually gonna turn this problem on its head. So we will specify the frequency pattern that we want and have our software automatically design a metasurface that satisfies um, your demands. So we can already do this sort of inverse design or generative AI for photonic integrated circuits, shown here, and we are gonna have this capability for metasurfaces as well. So our whole goal is uh, generative AI for Maxwell's equations. So there you have it. Hope this helped you, and please subscribe. Bye.